Hi everyone, and welcome back to another session of trying to solve some inverse Laplace transform problems. So this time we're going to concentrate on trying to go pretty quickly. So this is going to be pretty brisk. Feel free to pause at any time, of course, to try and figure them out for yourself. And I'm just going to try and run through a few of these, and we'll try something a little bit different at the end with the shift operator. All right, so to begin with, we have the inverse Laplace transform of 1 over s plus 7. So just to be certain about things, this is the inverse Laplace transform of 1 over s minus negative 7. So that should be e to the minus 7t. Done, right? As usual, t greater than or equal to 0. All right, moving on. All right, next one. We've got the inverse Laplace transform of 7s plus 5 over s squared plus 4. In this case, we're going to break it up into two parts. We may as well leave it all inside here. Inverse Laplace transform of 7 times s over s squared plus 4 plus 5 times 1 over s squared plus 4. We know that we want this to be 2, however, at the top in order to match with the form for sine. So we're going to have a 2 there and a 2 there. And once we've done that, we can go straight to our solution. This will be equal to 7 cosine of 2t plus 5 halves sine of 2t. Okay, hopefully that's clear. If that's not so clear, go back to the first video or try some from the textbook, see if you can kind of build up a little bit of this facility so that we can quickly get through them. Because remember, speed is always nice. Speed with accuracy is always good. All right, this time we have the inverse Laplace transform of 3 plus s over 4 minus s squared. In this case, we should recognize that this looks very much like hyperbolic sine and cosine could be involved. So we're going to rewrite this guy as the inverse Laplace transform of negative 3 times 1 over s squared minus 4, right? The negative so that we can switch the denominator there. And then plus s over s squared minus 4. And we can make some adjustments here. We want a 2 on the top there, so we're going to put that there and then have the divided by 2 in front of it. And we can go straight to our solution now. We get negative 3 halves sinh of 2t. Let's get that right. Of 2t plus of 2t. And that's it. So you could rewrite this in terms of the exponents if you wanted to. That would be e to the 2t minus e to the minus 2t over 2 plus e to the 2t plus e to the minus 2t over 2. And let's see, minus 3/4 plus 1/2 minus 1/4 e to the 2t, and 3/4 plus 1/2, so it looks like plus 5/4 e to the minus 2t. And again, alternate here to get to the same place would be partial fractions. I, of course, always prefer the fast way, if at all possible, as long as we can maintain that accuracy. All right, something a little bit different here. We're going to be looking at the inverse Laplace transform of 3s to the minus 1 times e to the minus 2s. So we have a combination of a rational function and an exponential. Now, the exponential should always put off warning signs that you might be doing a shift, because that's something that came up in our shift function. So let's rewrite this a little bit, see where we get to. We get the inverse Laplace transform of 3 over s times e to the minus 2s. So now let's try and recognize what we have here. So first of all, this is, right, we know that the inverse Laplace transform of this is 3 times the Heaviside function, step function h of t. And then this guy is, from the shift theorem, this should be telling us to substitute t minus 2 and multiply by h of t minus 2, the Heaviside function again. So if we put that together, this should be telling us that what we have here is 3h of t minus 2, right? That's substituting t minus 2 into this thing that we had from the rest of the function there, and then multiply by h of t minus 2. Now, this function is equal to 1 for t greater than or equal to 2, and 0 for t less than 2. And they're both like that. They're multiplied by each other. So we just get one of these things. This is equal to 3h of t minus 2. So if we were to graph that, this would be a function like this. It would be equal to 0 all the way up to 2. And then it would become 3 times 1 is 3 every time after that. Right? This is 3h of t minus 2. And that's the function whose Laplace transform is the thing that we started with there. All right, one more time. One more problem here with the inverse Laplace transform. Now we're going to do something with the other shift function. And so the other shift function told us the following thing. Just want to recall. It said that the Laplace transform of, the inverse Laplace transform of, let's word this properly. So the theorem that we have seen says that the Laplace transform of e to the at times f of t is equal to f of s minus a, where f is the Laplace transform of little f. But that means conversely that the inverse Laplace transform of f of s minus a is equal to e to the at times f of t. So basically we can shift the Laplace transform, the s function, at the cost of multiplying the eventual result by e to the at. All right, let's see how that applies in the case that we're dealing with here. Up top, we have inverse Laplace transform of s minus 4. And then if we complete the square in the bottom here, we get s minus 3 squared plus 2. Sorry, plus 4. Excuse me, I'm getting ahead of myself a little bit. Plus 4. Now you'll notice that this looks like it might be a sine or cosine kind of thing, but with this s minus 3 involved. So we can deal with it as it is right here, or we can be a little bit clever about it. But let's try breaking it up a little bit. We have an s minus 3 here. For the cosine formula, we also need the s on top, but we're going to need the same s minus 3 on top. So that would look like the inverse Laplace transform of s minus 3 over s minus 3 squared plus 4 minus, we still have a 1, s minus 3 squared plus 4. Right, so that first one looks exactly like cosine. It looks like the Laplace transform of cosine of 2t, except it's been shifted by 3 units, which means we would need to multiply by e to the 3t. The second one, we have to make a bit of an adjustment. We'd have to make it a 1/2 in front and a 2 here in order to make it match up. But if we do that, then this now looks like minus 1/2, and it looks like sine of 2t. But again, because of the shift, we would have to multiply by e to the 3t. And that is our inverse Laplace transform. There's a lot going on there, and I think the only way to really get your head around this is to work through a few of them and see how this works. There is a slightly different approach that we could take, which is to say, well, I had inverse Laplace transform of s minus 4 over s minus 3 squared plus 4. Basically, I could take the s's we replace the s's by s plus 3, and that to do that at the same time, I'd have to multiply by e to the 3t on the outside. Right? Basically, that's what this is saying. I can shift it a little bit, right? Because this here, if we extend that formula a little bit, that's equal to e to the at f of s, or should say inverse Laplace transform of f of s. So basically you can take s minus a and replace it with s, which is the same as saying take s and replace it with s plus 3. So this would become e to the 3t inverse Laplace transform of s plus 3 minus 4 over s plus 3 minus 3 squared plus 4 is e to the 3t inverse Laplace transform of s minus 1 over s squared plus 4. And with our practice now, we can see that that is, the first part is going to be cosine of 2t, and then the second part is going to be 1/2 sine of 2t. All right, so a little bit strange, this one, worth going back and looking at a couple of times. Work it out on your own as you can. Remember, we're thinking here about the shift theorems, so worth taking a look back at that video as well. All right, hopefully this is useful. Open your eyes to a few of the different possibilities.